Hello everyone, I am Kausal Patel from Mechanical Engineering Department at Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. In this video, we are going to discuss about the methods to determine the equation of motion for a given system. Then we are going to also derive the equation of motion using free body diagram method or equilibrium method using D'Alembert's principle. Okay, in this video we have also discussed about what is static equilibrium, what is dynamic equilibrium, what are the difference between them, and D'Alembert's principle. Determination of natural frequency. Now, to determine natural frequency of the system, there are three methods which we can use. First one, that is equilibrium method, second one energy method, and then release method. So in equilibrium method we need to draw free body diagram of the system. So it is also known as FBD method. So by using these three different methods we can determine natural frequency of the system. Okay, now we are going to determine the equation of motion using FBD method, or we can say equilibrium method. So here FBD method is based on D'Alembert's principle. So first of all we need to understand what is D'Alembert's principle. So the D'Alembert's principle is used to analyze the system which is not in dynamic equilibrium. Okay, so according to D'Alembert's principle, a system which is not in dynamic equilibrium due to some acceleration it possesses, it can be brought into dynamic equilibrium by simply introducing the inertia force acting on it. So we already know what are the conditions for static equilibrium and dynamic equilibrium. Okay, a system can be called to be in static equilibrium if it remains at its rest under the action of all the external forces and its velocity remains 0. It means it does not accelerate. So that system is called to be in static equilibrium. Now a system is called to be in dynamic equilibrium if the velocity of the body remains constant under the action of all the external forces acting on the system. So in this case it is also not going to accelerate and the velocity remains constant. Then the system is called to be in dynamic equilibrium. Okay, so it is obvious that if a body is subjected to force or torque, then it is going to accelerate. But in case of static equilibrium and dynamic equilibrium, its velocity remains constant. It is not going to accelerate. It means the summation of all the forces acting on the body, or the summation of all the torque or moment acting on that body, that should be 0. So that is the main condition for a system to be in static equilibrium or dynamic equilibrium. Total summation of force should be 0 and total summation of torque should be 0. Okay, so here as per the statement of D'Alembert's principle, a body or a system which is not in dynamic equilibrium or static equilibrium due to some acceleration it possesses, it can be brought into dynamic equilibrium or static equilibrium by simply introducing the inertia force or inertia couple. So here we are also going to apply the same condition. Total summation of force or total summation of torque should be 0. But here we need to consider inertia force and inertia couple, or we can say inertia torque. Okay, then we can consider the system is in static equilibrium or dynamic equilibrium. So now we need to understand what is inertia forces and inertia couple. Okay, so inertia force, it is an imaginary force which acts at a center of mass of the system, and its magnitude is equal to the product of its mass and acceleration, and its direction is in opposite sense that of an acceleration. Okay, so here inertia force is not real force, it is an imaginary force, and it is always acting at the center of mass of the system in the direction opposite to that of an acceleration. Okay, and the magnitude of inertia force, that would be equal to the product of mass and acceleration. Okay, so Fi is equal to m into a. So in the same way, inertia torque or inertia couple, it is an imaginary couple which acts about the center of mass of the system and is the equal of the product of mass moment of inertia about the center of mass and an angular acceleration, and its direction would also in the direction opposite that of an angular acceleration, right? So here inertia couple Ci, that could be written as the product of mass moment of inertia I about the center of gravity into an angular acceleration alpha. Okay, so here if the system is subjected to only forces, then we are going to consider a system to be in dynamic equilibrium if total summation of force along with inertia force would be 0, and if system is subjected to only torques, then we can consider the system to be in dynamic equilibrium if the total summation of all torques along with inertia torque, that would be 0, and if the system is subjected to both forces and torques or moments, then we need to consider both conditions. Then and then we can consider the system is in dynamic equilibrium. So as per D'Alembert's principle, total summation of inertia force plus total summation of all the external force should be 0, and total summation of inertia couple plus total summation of all the external torques, that should be 0. So these are two conditions for a system to be in dynamically equilibrium. Okay, now we are going to apply D'Alembert's principle to find out natural frequency of the system having single degree of freedom. Okay, so for that we are going to consider a simple spring mass system which is restricted to move only vertically. Okay, so initially the spring having stiffness K is taken, its free length would be this much. Okay, now one end of spring is fixed and at the second end a mass having m kg is suspended, so that the spring is going to be extended, it is going to be deflected through this much deflection, let it be delta, that is the static deflection of spring. So now as it is deflected through delta, this would be the second condition in which the system is not in motion, its velocity is 0 and it remains in its state of 0 velocity. So it means at this condition the system is in static equilibrium, right? So we already know what is the condition for static equilibrium, and that is total summation of force should be 0 and total summation of torque should be 0. Here we already know that at this state the system is subjected to two forces. First one, that is due to weight, and it is equal to mg, and it is acting in downward direction, while due to the deflection of spring, the spring force is acting in upward direction and its magnitude depends on the stiffness of spring. Okay, so here the spring force is acting in upward direction, let it be K into delta. Okay, so under the action of these two forces, the system is in static equilibrium. So it means the magnitude of weight and spring force, that would be equal, but both forces are acting in opposite direction, so they are going to neutralize the effects of each other. So here, for this static equilibrium condition, we can write down mg is equal to k into delta. So these two forces can be neglected in the further analysis, as they are going to neutralize the effect of each other. But in this theory, we are going to consider both the forces. Okay, now the system is in static equilibrium in this position, right? Now let it be deflected by applying external force in downward direction. So under the action of that accelerating force, let it be deflected through x distance at particular instant of time. Okay, so here the spring is further extended through this much distance x. So during that motion, the system is having acceleration in downward direction, and that's why the system is no longer remain in static equilibrium or dynamic equilibrium. Okay, so for this instant of time, whenever the system is deflected through x distance from its mean position, okay, this would be the mean position of the system. Okay, so at that instant of time, we need to analyze the system. So here the system is not in dynamic equilibrium due to some acceleration it possesses. So in that case, we can consider the system is in dynamic equilibrium by considering inertia force acting in the opposite direction to that of motion. Okay, so here acceleration is in downward direction, so inertia force would be acting in upward direction, and its magnitude would be mass into acceleration. Okay, so in this free body diagram, mass m is drawn, okay, and all the forces acting on that mass are represented. So gravitational force is acting in downward direction. Okay, in upward direction, spring force is taken as k into x plus delta, as here we know that the total deflection of spring, that is x plus delta. So that's why total spring force acting in upward direction, that is k into x plus delta. Now inertia force is acting in upward direction, so this would be our free body diagram. Okay, now for this free body diagram, we can apply D'Alembert principle. Okay, but before that, we need to choose force convention. Okay, you can choose any of force convention. You can choose a force convention in which upward forces are considered as negative and downward forces are as positive. You can also consider a force convention in which upward forces as positive and downward forces as negative. Okay, in the similar manner, if the system is subjected to torque or moment, then you can choose a force convention in which clockwise moment as negative and counterclockwise moment as positive. Okay, otherwise you can also choose clockwise as positive and counterclockwise as negative. So the choice is yours. You will get the same results. Okay, so if we are going to choose downward forces as positive and upward as negative, then from this free body diagram we can write down minus mx double dot minus k into x plus delta plus mg is equal to 0. So here, as per D'Alembert's principle, the total summation of force along with inertia force, that would be 0. Okay, this part already we have discussed. So here the force convention is chosen as downward as negative and upward as positive. So here upward forces are inertia forces mx double dot and spring force k into x plus delta. Okay, they are considered as positive, while mg weight is considered as negative. So we can write down mx double dot plus k into x plus delta minus mg is equal to 0. Okay, now we can simplify the equation and it is reduced to mx double dot plus kx plus k into delta minus mg is equal to 0. Okay, so here we already know that the spring force due to static deflection k into delta, that is equal to mg, and they are going to neutralize the effect of each other. So we can eliminate these two forces, and finally our equation is reduced to mx double dot plus kx is equal to 0. So finally the equation could be written as x double dot plus k by m times x is equal to 0, and this is the equation of motion for simple spring mass system. So here we can see that the equation is quite similar to the equation of simple harmonic motion which we have derived earlier. So the equation of simple harmonic motion, that is x double dot plus omega square x is equal to 0. Now by comparing these two equations, our equation of motion and equation of simple harmonic motion, we can get omega square is equal to k divided by m. So ultimately we can write down omega is equal to in square root of k by m. Here omega, that is nothing but the natural frequency of the system, and that's why we have denoted it as omega n. Okay, so for simple spring mass system, this would be the equation of natural frequency, and it depends on the stiffness of system and mass of the system. So here the natural frequency omega n is equal to in square root of k by m, which is measured in radian per second. Now to convert the radian per second into the cycle per second, that is nothing but hertz. So to find out natural frequency in hertz, we have to divide natural frequency omega n with twice pi, as we already know that in one cycle there is a twice pi radian. So that's why to find out frequency in hertz, or we can say cycle per second, we have to divide omega n with twice pi. So here the frequency in hertz could be written as fn is equal to omega n divided by twice pi, and is equal to 1 upon twice pi in square root of k by m. Okay, now periodic time, that is another important parameter, and we already know that it is nothing but the time taken to complete one cycle. So it is nothing but the reciprocal of natural frequency in hertz, because hertz is nothing but cycle per second, and we need to find out periodic time in second per cycle. It means time taken to complete one cycle. So it is nothing but the inverse function of frequency in hertz. So ultimately time period tau p could be written as 1 upon fn is equal to twice pi in square root of m by k second.